Welcome to Web Handling. My name is Dave Roysum. This is a continuation of a mini-series on human factors for web machines, a subject that is ripe for major reform, and I am happy to be at the front of it. In this fifth clip, we move on to the essence of industrial controls. Here, we dissect options for set-pointed feedback, such as might be used by a tension controller or a thermostat. Let's start by making a list of needs and wants. We absolutely need a set point. For web machines, each set point needs to be in engineering units. These units must be calibrated and calibratable per instructions in the service manual. Otherwise, reproducibility with time and between machines is compromised. Also, for the same reasons of reproducibility and trustworthiness, we need a sensor feedback reading in numbers. The feedback reading also needs to be calibrated in the same engineering units as the set point, as well as calibratable per instructions in the service manual. If we want, we might also consider graphics, because this can increase the speed and accuracy of operator comprehension. We might also give the operators visible limits so that they know what is allowable. If we really feel this particular parameter is important, we might add graphing for troubleshooting. Finally, we can add recipes to help ensure consistency between runs and for a given grade. So let us take a look at a commercial tension controller in the next slide. This controller is the poster child of way too many buttons. There are more than 24 buttons and readouts, primarily because they made the major sin of putting operator and maintenance controls on the same page. It reeks of geek. The previous controller was discontinued for good reasons. It is a control abortion. The upgraded model shown here is a slight improvement by virtue of half the knobs and buttons. Still, it is neither intuitive nor pretty. It also commits newbie errors such as putting up-down arrows side by side and many other such arrangement faux pas. So let's see if we can find anything better in models from the competition. The one on the left suffers from almost as much busyness as the first model we showed. It also reeks of geek. It also has terrible choices of font sizes that requires bifocals with a close stance to read the inputs. The one on the right accomplishes exactly the same functions, yet has far fewer buttons and knobs. Still, the arrangement is not intuitive. We also should do a time study to see how often and how quickly the operator would need to change tension to see if a virtual or a physical knob would be better. So, let's check with some more name brand models to see if there's one we can use as a model of ergonomics. Here, we are now beginning to pare down the number of numbers, buttons, and knobs, but the inputs are still not intuitive. Also, the portrait orientation and odd aspect ratio of the one on the left adds to ugliness. Worse yet, if you are not ever vigilant, the square edges will take a chunk out of your shoulder as you walk by. This one looked like the engineer just discovered a new programming tool set and was going to add everything in that toolbox to make the box modern looking. Unfortunately, in the process, we now have as much knob and button confusion as we started with in the first example. The only improvement is that we finally have something that is beginning to look pretty. Still, it looks to be pretty unusable without an engineering degree and an instruction manual to go with it. After a half an hour of searching on the internet, I was still unable to find a good model of tension controller to illustrate good ergonomics. Thus, I turned to other applications to see what we might learn. Here we look at a simple thermostat. We all remember the clock face controller, set point and feedback on the same simple device. Still, it is not ergonomic because the set point and feedback are on opposite sides of the clock. At least they were smart enough to put the set point on the top so that you don't cover it as you turn to a new temperature. Other problems include the tiny switch to set AC, heat, and off, and that you have no idea whether the heater or air conditioning is running. So next, we tried an internet search to see what modern alternatives might teach us. This popular clock face device looks similar and does give a color-coded feedback as to the state of the heater or air conditioner. However, it is so pared down so as to how to program it is not obvious. Using it will require an instruction manual. Sorry, not included. You will need to go to the internet. Oh, but did I mention, you can control it with a smartphone, if you're smart enough. Finally, in frustration, I offer my own controller as an exercise in applying good ergonomic principles to a device that is in many ways similar to a tension controller. Here, the setting arrow, shape, color, and placement all reinforce what the buttons do. The setting buttons are next to the display line, which is to the left so our hand does not cover it. The bottom button toggles the mode that is reinforced by the display right next to it. The status of the appliances are shown with either icons or a light embedded in a color-coded overlay. Here, the heater is shown running and the AC, of course, is not running. Finally, if you really want to get fancy, you could give a color gradient thermometer with set points and feedbacks clearly shown. Of course, when possible, the aspect ratio should be the 3:4 in landscape orientation. Looks matter, and they seldom cost much, provided that you do your homework up front. We will use this exercise to move on to a more complex control. That is, the TNT settings on a winder that does not have taper or roll structure or curves. From our Web 101 class, we know that the knobs that control tightness are known as the TNTs of winding. These stand for tension, nip, and torque. We will order the knobs in that conventional order. That order, by the way, is also the order of most to least frequently found on winders. If we include speed, then we might consider a physical knob. Of course, the one shown here would not at all be suitable because it is not shown with calibrated engineering units. Each bar graph clearly shows the strength of each knob, which is the height of the bar. An operator could see this from 10 feet or even 10 meters away. Not just any individual control, but also the common running shape will be easily remembered visually. The actual feedback are the heavy dotted lines. The light dotted lines represent upper and lower limits, if applicable, due to machine or recipe limitations. At this point, you are right to ask, why not show the feedback as numbers, as we did for the set point? If you have ever looked at a responsive tension meter, you would instantly know why. Flickering numbers are not something you are going to write down. If you need to, take a data recording off the instrument, or merely record it with a cell phone camera. However, if you are totally sold on geek, you could add a feedback number below the set point number. To the right of the output display, we have a 5-position rocker knob that runs the setting display above. Presumably, we could change set points on the top screen by simply arrowing right or left, and then setting by arrowing up or down. Screens below the top screen could store recipes and other tech. Wait a minute, you say. What if the operator needs to change tension quickly for some reason? Well, if that were frequently the case, you would want a physical knob such as we had for speed. However, that is usually not the case for tension and nip or torque. Still, we can make an adjustment pretty quickly on the home screen. Just select tension via the rocker switch left and right and leave it set there. If you need to change tension, just rocker up or down. A mini joystick is even faster than a rocker, as any gamer will easily attest to, though the enter button takes a second hand. The well-studied reader, especially those who have taken my Web 101 course, will know that this control is not suitable or sufficient for a modern winder because it lacks taper or curves. However, 99% of web machine controls do not need curves, and thus this serves as a template. A more legitimate critique is that we lack graphing that might be useful for diagnostics. We can adopt the previous convention and merely add graphing off to the left. Again, the rocker and top screen sets the parameters. The screen below the home page could adjust starting and ending times for the data recording display. So, what can we learn from this exercise beyond the fact that finding examples of good control ergonomics is quite challenging? The overriding concern is fewest. Fewest input devices to get the job done, fewest button punches to get common operations done, fewest words and numbers, provided that they show calibrated units, fewest pretty much everything with one exception. You have to get the everyday job done without going to the internet for instructions. We can add features if it enhances the operator's performance. Here we added graphics, specifically bar graphs, as they are more ergonomic than speedometer dials. On those at a glance intuitive bar graphs, we added feedback, upper and lower limits, and even graphing. Finally, let's not forget the art of beautiful design. Pleasing shapes, pleasing rounded corners, sizes, colors, and so on should be incorporated by a team of 3. Those are industrial design artist, controls engineer, and operator. If a brand new operator can't figure it out within 60 seconds without instruction, it needs to go back to the drawing board. If a new engineer who never saw the device before can't reprogram it from a standing start or recalibrate it or draw data from it in less than 60 minutes, it needs to go back to the drawing board. Experienced users should accomplish all of those tasks in 1/10 of those above times. Thank you so very much for watching this module in my Plant Practical video series. Stay tuned for the next clip where we will continue to outline our best practices of HMI controls for web machines. Be sure to like and share. See you next time.